Hello, pre-calc students. This is Mr. Beck. Today we're going to be talking about exponential functions. Kind of like going through a history of different functions that we've referred to. We've talked about linear functions, quadratic functions, talked about general polynomial functions. We talked about rational functions. Now we're going to be talking about the last series of functions, and those would be beginning with exponential functions. Now, if you remember in 5.1, we talked about composition of functions, and then excuse me, what we did with those functions, we had like one function within another function. Then we talked about one-to-one functions, and one-to-one functions, if you have a one-to-one function that has an inverse. So using that kind of mentality, we're talking about 5.3. 5.3, we're talking about exponential functions, and then its inverse, because exponentials are one-to-one functions. Its inverse is a logarithm function, and we're going to begin to do a little bit of work with logarithms as well. So let's get into it. Exponential function is a function that generically has this form, f of x equals c times a to the x. Now, a is what we call the base. An example of this would be f of x is 2 times 3 to the x, where 3 is our exponential base. 2 is going to be that ends up being a dilation, but that 3 is that exponential base that we really want to care about the most. Now, what's important about this base, this a value must be greater than 0. If a is not greater than 0, then we start ending up with some pretty extreme cases. And in fact, it's hard for graphing utilities to actually graph that function, because sometimes you have positive values, sometimes you have negative values, sometimes you have imaginary values. So it comes down to, we define it as a is greater than 0. Now, a is not allowed to equal 1, because if a does equal 1, then we're going to have a horizontal line. And c is not equal to 0, because once again, we would have a horizontal line of that. So that base a we do call the growth factor, and that's the growth factor only if a is greater than 1. If a is less than 1 or between 0 and 1, that's what we call the decay factor. We'll get to those kind of problems later. Now, we look at this as any f of any x value divided by f of the previous integer ends up being a, and this a is what we call a ratio. That ratio is going to, we look at this more when it comes to geometric sequences. So with geometric sequences, we have any term to its previous term, that ratio ends up being a. So c is our initial value, since f of 0 ends up just equaling c, like we can see here, because a to the 0 is 1. So the first series of problems that we have are, can we determine the difference between exponential functions and linear functions, whether it's arithmetic or geometric sequences, if these were indeed sequences. So when you take a look at these points, one of the things I'm going to look at is what's the common difference between these. And the reason why I'm looking at that is because I have kind of an arithmetic sequence in mind. Arithmetic sequences do have a common difference. That common difference ends up being -3 for each one of these. 2 minus 5 over 0 plus 1. -1 minus 2 over 1 minus 0. So -1 minus 2 over 1 minus 0 does give us, honestly, it gives us a slope of -3. And the fact that we have a common slope throughout each one of these series of points means we do have an arithmetic sequence, which is a linear function. Now, because we are given the y-intercept, and that would be f of 0, it's a lot easier for us to just put this into slope-intercept form, because we have our slope of -3, aka common difference, and then we have our y-intercept of 2. Now, if we look at this problem, we look to see what a common difference is. This difference is -54. This difference is -18. This difference is -6. So we definitely do not have a common difference or a common rate of change. What we do have is a common ratio, and I have that highlighted up here. If we take the ratio of any one of these terms divided by the previous term, we end up getting that common ratio of 1/3. So the common ratio of 1/3 is our base of our exponential function, also known as a geometric sequence if we have this in a sequence form. And then the leading coefficient, that c value, is going to be our y-intercept, so 27. So some properties of exponential functions. If we have exponential growth, which is what happens when a is greater than 1, we do have a graph that looks like this. Now, something that I do want to note, what is the limit as x approaches -infinity? So when x approaches -infinity, we're talking about this point on the graph. And we can see that we have a horizontal asymptote, and that horizontal asymptote is y equals 0. What's the limit as x approaches positive infinity? of f of x that is also positive infinity because this graph goes up forever. Domain of this function is all real numbers. Domain of every exponential is all reals. Range is going to be all the y values above the horizontal asymptote. For our basic case, which we have right here, I think I covered the f. For our basic case that we have right here, we don't have any vertical shifts, so it's just y is greater than 0. We do know that this is an increasing one-to-one function. And again, the reason why we care about this being a one-to-one function is because this is also going to have an inverse function. That inverse function is going to be the logarithm. And I keep mentioning it, but we're going to be talking more about it today. So last but not least, these 3 points that I'm going to have you guys graph, -1, 1 over a, 0, 1, and 1a, those 3 points are going to be the 3 key points that I'm looking for. And the reason why I'm looking for that is because on our graph, that is usually where we're going to see the curvature of that exponential growth the most. So I care about those 3 points because they typically will show that. They don't always, but typically they do. So take a look at this. How do I graph these problems? The very first thing I do is I look for the horizontal asymptote. That horizontal asymptote is going to be my vertical shift. So because that vertical shift is -2, and for those of you wondering what I'm talking about, if I have f of x equals a times b to the x minus h plus k, that vertical shift is going to give us our horizontal asymptote shift. So the first thing I graph is that horizontal asymptote. The second thing I do is I look to see, is this growth or decay? If this is growth or decay, basically what's the shape of this graph? We have 4 basic shapes that we're going to be looking for. We have growth that will look like this, which is our typical growth. And then if we have a reflection of that growth, kind of like debt, a reflection of that growth is still going to be more like a negative growth. But I want to know basically what the shape's going to look like. That way, when I plot my points, and then my points are where my exponent equals -1, 0, and 1. When I plot those 3 points, then I fit the shape of the graph along the asymptote through those points to create the entire graph. Now, when it comes to this one, horizontal asymptote, once again, we're going to look at what is our vertical shift. So y equals 6 is our horizontal asymptote. Then we figure out what makes the exponent -1, 0, and 1. So officially, we could do this. We could always set the exponent that we're given there equal to -1, 0, and 1. Hopefully, these are simple enough problems, or this one's a simple enough problem that you can plug in 2, 3, and 4 because you recognize that's what makes the exponent -1, 0, and 1. Plotting our y values. Plotting our y values gives us these 3 points. And can we fit these 3 points to a negative growth graph? So looks like so. Now, one of the things that these problems are asking is what's the domain and range? Domain of every exponential function is all reals. The range, since this is positive growth, that range is going to be from the asymptote to infinity. And problem number 4 is negative growth. And negative growth ends up giving us a range from -infinity to 6. Please, please, please don't ever say 6 to -infinity. It's always going to be the lower number to the higher number. Moving right along. We do have exponential functions also that have a base that's between 0 and 1. If that base is between 0 and 1, that's what we call exponential decay. Most common form of exponential decay that we could talk about is maybe radioactive decay in the science world. How about if you ever purchase a car, cars depreciate in value. So when anything depreciates, you have exponential decay of that as well. Once again, the domain is going to be all reals. So when it comes to every exponential function, the domain is always going to be all real numbers. The range is still going to be the y values greater than 0. Now, what happens with our decay? We have one of 2 graphs occurring. First graph that could occur is going to be an exponential decay graph looking like that. Or if we have negative decay, that means that it approaches a certain y value. So that negative decay ends up being a reflection over the x-axis. Now, the limit as x approaches negative infinity is going to be positive infinity. That would be for the positive growth because we're talking about that part of the graph right there. Now, as x goes to positive infinity, we end up with the y value of 0. That's what creates the horizontal asymptote of y equals 0, this time in the positive direction. Once again, we do want our exponents to be -1, 0, and 1. By having them as -1, 0, and 1, that allows us to find those three key points again. And every exponential function is smooth and continuous. I know I didn't say that on the first one. That's kind of our calculus way of saying, hey, we can find the derivative of this. Now, it's not calculus, so let's go into pre-calc. Kind of like before, the very first thing I look for is there a vertical shift? No, there's not. So the horizontal asymptote is y equals 0. Now, this is a positive decay. Since it's positive decay, it looks like so. Plug in -1, 0, and 1, and we get these 3 points that we fit the positive decay graph in. Same thing over here. Very first thing I look for is the horizontal asymptote of y equals -4. Now, we can tell this is decay, and this is positive decay, so it will look like so. And then plug in what makes the exponent -1, 0, and 1. And once again, just to show something like that, I am going to set x plus 2 equal to -1 and solve. That's how I get the x coordinate -3. I can set it equal to 0. I can set it equal to 1. And that's how I get my 3 x values. So the horizontal asymptote is y equals -4 down here. Oops, used the wrong tool on that. Did not mean to erase. Y equals -4. Plot these 3 points. And this is going to be the first case. I know I didn't really do it on the other problem. But how do we find our y-intercept? So I did that in red on the graph. So what is f of 0? F of 0 is going to be 1/3 squared, which is 1/9. So 3 halves times 1/9 minus 4 gives us -3 and 5/6. So there's our y-intercept. Domain and range. Domain's all reals for these two. The range is going to be from the asymptote to infinity, from the asymptote to infinity. Now this one also has a positive decay. Same thing is occurring. What's our horizontal asymptote? We get that right there. What makes our exponent -1, 0, and 1? In case I didn't realize it, -x plus 3 equals -1, so -x is -4, which means x equals 4. So that's how I got that point, actually. So what makes the exponent -1, 0, and 1? And if there's any questions about this, please let me know. Most people are okay with this. Now, next problem that I'm looking for is if I give you the equation, but I don't give you the graph of it, or don't expect you to graph, can you come up with all the key details? And that's really what I'm hoping for. I'm hoping that you could look at this problem and say, hey, I recognize that is an exponential function. And more importantly, I know that since this is between 0 and 1, I know that this is a decay graph. I do know that it's reflected over the x-axis due to that negative out in front. Horizontal asymptote is -7 and shifted to the right 6. Now, I'm hoping you could look at the equation like I just did. Now, let's answer the questions. Domain's all reals because it's an exponential function. I'm not sure why that turned into an arrow, but okay. The range is going to be from -infinity to -7, and that's because we had that reflected decay graph, or negative decay graph is what I said. Our decay factor is 0.9 because it's going to be whatever that base is. So whether you have a growth factor or decay factor, that factor is going to be the base. This next problem, I have a real life situation where I have rumors that grow based on the number of people that we have n. The rumor will grow based off of whatever the initial population is and how many days have elapsed. That's what D represents. So in a school of 5,400, what would happen is the number of people who hear a rumor would be 5,400 times 1 minus e to the negative 0.015 times 12 days. So when we do that, we get 890. Now this problem actually gives us like 889.5 if we do that in a calculator. You can either round up or round down. I would fully accept 889 students because maybe that last person has not fully heard the rumor after 12 days. You could argue they've been sort of told the rumor, so maybe they've heard something. Not going to worry about it. Just give me 889 or 890. Now, what is the limit as d approaches infinity? That limit as d approaches infinity ends up being 5,400. We can figure that out by plugging in some very large values for d right there. Now, why is that so? because if you see what I have here, what I have here is going to be just kind of distributed. It shows a little bit more of the nature of this P ends up being the horizontal asymptote because that's our vertical shift. Then this ends up being some decay because e to a negative power ends up giving us decay. And then that negative out in front means it's reflected. So we have that decay initially, reflected gives us that kind of graph. So when enough time has passed, everyone's heard the rumor and everyone would be 5,400 in this case. So next problem, if we have 500 vocabulary words to learn, basically a formula. One of the things that I care for, or that I ask you to be very careful of, is units where t is in minutes, but I ask about a half hour. So you're really saying what's f 30, and then an hour is f 60. Now, one of the things that this should show is that in the first 60 minutes, or first 30 minutes, we learned 84 words. In the next 34 minutes, we learned some quick subtraction skills. That would be 49 words. So you can see that we're learning fewer and fewer words, which is the idea behind decay or exponential decay. How do we graph this? I noticed that the graph's not there, so we're going to do this manually. What makes the exponent -1, 0, and 1? That'd be the x values of 0, 1, and 2. Horizontal asymptote is y equals 2. So e to the negative first is 0.368. So that's 0.368 plus 2, which is 2.368. E to the first is, or e to the 0, because it's 1 minus 1, is 1. 1 plus 2 is 3. Then e to the first power, e is 2.71828 plus 2 gives us 4.718. So we have a graph that looks like so. Now, I knew those values off the top of my head because I'm a math teacher. I fully expect some students to actually plug in all of those values and see what happens. Make sure you know how to use your calculator to plug in those values. Moving right along, we have exponent laws. Now, we call these laws because this is really how the number system works. I don't like to say rules because rules are like, hey, let's create this thing just to show you this is what you need to do to stick within the parameters. These are laws. The reason why these are laws is because why does this property work? So this exponent law is if we multiply the same base, then we just add the exponents. One of the ideas behind it is let's just say what is 2 to the third times 2 to the fifth? This means we have 3 multiplications of 2's. This means we have 5 multiplications of 2's. And so when we multiply everything together, then we have a total of 3 of them here and 5 of them here, or 8 total multiplications. So exponents really simplify multiplication, which is why multiplying the same base, we add those exponents. In a situation like this, if I have 2 to the third, I have that to the fourth power. That's 2 to the third times 2 to the third times 2 to the third times 2 to the third. Basically, we'll say that's 2 to the third, but we have 4 3's, so it's multiplication. So once again, based off of the way numbers work and how we assign these properties to these numbers, it makes it a consistent system. This exponent law, this is our distribution property, so we could distribute that exponent to each individual factor. And the reason why is because exponents simplify multiplication. Exponents do not simplify addition, which is why a plus b to the t does not equal a to the t plus b to the t. Really, exponents simplify multiplication, not addition. So definitely don't do what we commonly refer to as the freshman theorem. So moving right along. 1 to any power is 1. Then we have this law. Basically, if we have any base to a negative exponent, then it reciprocates that base. We sort of use that property already, so most students seem to not really have much of an issue with that. So moving right along. That anything to the 0 power, oh no, it jumped on me. Anything to the 0 power is 1. And if a to the u equals a to the v, then u equals v. This is something that we're going to talk a little bit more extensively about. By the way, this is only true if a does not equal -1, 0, and 1. So when it comes to, a is not allowed to be negative because, negative base. But anyway, this is something I'm going to show you why this works. And it's not just about that this happens. I'm going to show you why this works, and that's going to be our primary focus. So let's get into our problems. First problem, 3 to the x plus 17 equals 9. So most students are like, hey, I know how to do this. We get 3 to the x plus 17 equals 3 squared. Using that last property, we jump down to x plus 17 equals 2, which makes sense because if they're the same base, then their exponents are the same. And then we solve for x. What I care more about is why does this work? And this is where, what's the algebraic way that we get from this step right here? So how do we get from this step right here down to the final answer? Comes down to how do we undo an exponential base? And that is the purpose of a logarithm. A logarithm is defined as the inverse of an exponential. So it's pretty much straightforward right there. Says the whole goal of this is to invert, and it inverts an exponential. Well, how do you invert an exponential? Kind of like a hard thing to picture and say what's going on, but it undoes it. It's like addition undoes subtraction, multiplication undoes division, squaring undoes the square root, cubing undoes the cube root. If we have an exponential base, what undoes that exponential base? That's what a logarithm is. Logarithms are like, they're really hard to explain what they are because their purpose is really to undo. So how do we undo a base 3? So how do we undo this base 3 right here? We undo the exponential base 3 with a logarithmic base 3. So this log base 3 undoes the exponential base 3 and gives us the exponent. And again, that's the whole point. That's what logarithms do. That's how they work. So the log base 3 undoes the exponential base 3, and we're left with 2. So what's happening is, and what I have in blue is, I will take log base 3 of both sides. So your step that I want you to think about taking is take log base 3 of both sides. So on problem B, we start by saying, hey, let's make these into a common base. And now we will take log base 3 of both sides. So let me undo what I just have there. I take not base 3. What undoes the exponential base 5? A log base 5. What undoes the exponential base 5 over here? Log base 5. And so you're left with just the exponent. 3, just the exponent of x squared. So x is positive or negative square root of 3. Now we should check just to make sure that this works, and it should because the domain of every exponential function is all real numbers. Since the domain of this is an exponential, the domain is all reals. Therefore, any solution that comes out of this should actually work, and it does. Level 2 problem. First, we have to make both sides into the common base. Both of these come from a base 3. Since they both come from a base 3, we can rewrite it. And notice how then we're going to have to use one of those exponential laws, multiply the exponents together, and then we will take log base 3 of both sides. And when we do that, we solve this. We end up with linear equaling to linear. Pretty easy to do. This one, once again, we have to find a common base between 4 and 8. That common base is 2. So if you see that I already multiplied this, this is 2 squared. So 2 to the 2 times 6x minus 7. That, I promise you, does say 6x. Doesn't really look like it, though. And then this is 2 to the negative third. So that one's pretty straightforward. And then how do we get from this step to this step? We will take log base 2 of both sides. And we get to our answer. Level 3 problems. Suddenly we're getting more and more complex, but still not too bad. 2 to each side, so that becomes 2 to the third to the 2x, so 2 to the 6x. Once again, we will take log base 2 of both sides. I'm not going to write this over and over, but I want you to know that that's the mechanism we use to undo that exponential base. So x squared plus 8 equals 6x, and then suddenly this now turns into a quadratic function. So if you remember at the beginning of our notes today, I said, okay, we have functions that are within functions. We have compositions of functions. We did that. I think I said 5.1, but I really think that's more 5.1. No, that is 5.1. But we have functions within functions. Now that we have the quadratic, we solve quadratics by factoring. Yay! I love quadratics. For this one, same kind of thing. You have to figure out 4 and 1/32. Both of those have a common base of 2. So 2 to the 2x squared minus 6 equals 2 to the negative 5x. Working from there, we solve. Now this one turns into, unfortunately, we're not able to solve by factoring. So thankfully, we have the quadratic formula that we could use. Negative b plus or minus square root of b squared minus 4ac all over 2a. Then we get to our level 4 problems, and everybody, I guarantee you that I'm going to ask you how to solve this level 4. The idea behind this level 4 is this is the direction of where we're taking it. This shows that you actually understand how to work with the exponential laws. So yes, you are going to be tested on this. So with that said, we begin by saying, hey, I have now multiple bases. So let's make this, all three of these into a common base, which is 3. And now we're going to use that exponent law up here, the one that I started. And the reason why I started is because I knew I was going to be using it, where we're multiplying the same base, so we add the exponent. So we are multiplying that same base of 3, which means we add the exponent. So 4x plus 3x squared. And then how do we get from here to here? We will take log base 3 of both sides. Now, one of the mistakes that I know that students make is they're like, oh, let's just cancel out all these 3's. And I'm like a big no. You do that, now write no on your paper because that's a foul. We have to undo both sides. We can't take this factor by factor. We have to take the log base 3 of both sides. That's what's important. So now we get into, once again, a quadratic. And this quadratic does factor, so we have two very nice solutions, negative 1/3 and negative 1. Now let's talk a little bit about an application. This is kind of like the prelude to working with logarithmic functions, because if I have 5 to the negative x equals 4, how can I use that to come up with other values? One of the approaches we could take is algebraically, how do we change both sides so that I turn from 5 to the negative x into 5 to the x? I could raise both sides to the negative first power. So I directly get 5 to the x equals 1/4. Now, how do I get from 5 to the x to 25 to the x? Well, 5 to the x, well, how about this? 25 to the x is equivalent to 5 to the 2x. So what I can do is on both sides, I can square both sides, so I get that 5 to the 2x power. So if I square 1/4, I get 1/16, and there's my answer. Over here, this is just kind of a way of merging the graphical and the algebraic to show why that it works. So I graph 2 to the negative x by making the exponents negative 1, 0, and 1. I graph 4 to the x plus 3 by making my exponents negative 1, 0, and 1. Plot those 3 points. I didn't actually show that, but plot those 3 points. We see that these intersect. The y value ends up being 4. That's not really the y value that I'm looking for as much as what's the x value that makes that y value 4. So that x value for both of these is negative 2. And so if we solve this algebraically, you can see that we set the two equations equal to each other, and then x ends up equaling negative 2, which, as I said, we saw before, but this is kind of like a nice way of showing why it actually works that way. And then we get into the beginning of logarithmic functions. When it comes to logarithmic functions, remember the purpose of a logarithm is the inverse of the exponential. Because it's the inverse, we could switch the x and the y, and so we get this x equals a to the y. We could write as y equals log base a of x. Now, I tend to not take that approach because, especially the goal with logarithms, we tend to solve these. So when solving these, what I ask myself is, if my goal is to use this logarithmic base 3 to undo 81, or at least to figure out what exponent this says that 81 is 3 to some power. And our goal is to figure out what power that is. Well, if I rewrite 81 as 3 to a power, that would be 3 to the 4th. The logarithmic base 3, once again, undoes the exponential base 3, and we end up with the value of 4. So the 64 is 4 to what power? That'd be 4 to the third. So log base 4 of 4 to the third is just 3. And next time we're going to see some properties that kind of make this a little bit clearer. But the reason why I talk about it this way is the whole point of the logarithm is to undo the exponential. So if you go into that mentality of saying, okay, 64 is 4 to the third, so log base 4, 4 to the third is just 3. This one gets a little trickier. We have 8 is 4 to what power? So a lot of people are like 2, and it's like, no, 4 squared is 16. So one of the things we have to do first is, how do we change 4 to the common base? The common base between these two numbers. That common base is 2. So how do we get 4 down to 2? We take the square root. So we do the root first, and then now that we're down to 2, we have, let me actually show that. So this is now log base 4 of 2 to what power? Gives me the 8 that I want, and that would be 3. So I always look at this and say, okay, I know that the common, or the base that we want is 4. So we have to take the root first and then take it to the power to get to that 8. So anyway, 3 halves is our answer. Log base 4 of 4 to the 3 halves is 3 halves. Same thing with this problem, log base 1/3 of 27. So I know 27 can be written as 1/3 to a power. To take 27 as 1/3 to a power, first thing we need to do is make the exponent negative, because now that turns that 1/3 into a 3. And then 3 to what power is 27? That's where the other 3 comes from. So -3. This one, log base square root of 2 of 64. So 64 is the square root of 2 to what power? I know that if I take the square root of 2 and square it, I get 2. But then I have to raise that to the 6th power to get 64. So we multiply the exponents to get 12. And last but not least, we have what's called natural log. Natural log is log base e. So this is log base e of e to the 5/6 power. So log base e undoes the exponential base e, and that gives us just 5/6. Now, just a very, very quick note on natural log and e. I know I skipped over it. I had that information right here. E is defined as its Euler's constant. So E is about 2.718281828, and then it goes 4 after that. So it doesn't actually repeat after that, which is kind of strange. I look at that and go, that's obviously a pattern, but no, it's not. Then there's a 4 afterwards. So E is about that number. It's the natural number. It's the natural rate of growth. On a calculus level, that the y value of the E function is the rate that it grows. So it grows at its own rate. That's why it's called the natural number. Since the E is the natural number, natural log is log base E. So hopefully you found this informative and you have a good direction on how to approach your homework. So take care and stay safe.